There it goes. So with chapter 13, we're looking at kinetics. So it's ultimately rates and motion, how things move, how molecules move and interact with each other to produce products. Okay? So there's some major topics that go along with this. We've got kind of the basics of kinetics. So what different new things show up in it. So we've got rates. We've already just mentioned that. We'll look at how concentrations and time and temperature can affect these things. Okay? So that's where we'll get into rate laws. How can we describe kinetics mathematically? Okay, remember how I said mathematics was a huge part of this? Kinetics plays or has a large math dependence. We'll look at time dependence. So what happens as we change the time with respect to the reaction? What information can that tell us about our rate laws? Okay? One of my favorite sections would be mechanisms. Okay? Once we have a rate law and we understand something about the rate, what does that tell us about how the reaction actually works? Which is ultimately going back to organic chemistry and trying to understand how individual molecules interact with each other. Okay? We don't quite take it that far in this class, unfortunately, but we'll look at how the mathematics can give us information about what steps are involved. Okay? And then the last thing, looking at energy dependence. So taking this back a little bit to the thermodynamics that you already understand, in theory understand, and see how that affects our rates. Okay, so we'll look at some pictures. So we've got a sequence of factors that affect our overall rates. Okay, we've got concentration, the nature of the reactant, mechanism, temperature, and then we can also throw in some catalysts. Okay, so these are all things that we're going to kind of address to varying extents when we move through this chapter. Okay? So you'll keep seeing this slide. Ultimately, they're the same kind of thing. Okay? So how do we quantify kinetics? So how do we quantify the study of motion? Okay, so one of the things that I tried to do at least twice is I bring in a bunch of beach balls, and of course they'd be inflated, and then toss them out into the crowd of students. And we could watch the kinetics of beach balls bouncing through the classroom. Fortunately, this is really, really early, and it isn't a graduation ceremony. So ultimately, what happens to the beach balls? They fall very, very quickly to the ground. And I get all excited about throwing the beach ball out and wanting to see everything jump around the classroom, and I see the beach ball just hit the ground. One case, I think it actually hit a student straight in the face, and it just hit the ground. Okay, well, that kind of defeated the purpose of this activity. So we stopped doing that. Okay? So we'll use our imaginations with beach balls floating through the classroom. Okay? And we could describe how those beach balls shifted and moved through our individual classroom and what things could contribute to that. So we could look at the movement. How does that beach ball move? Okay? How fast is it moving? What direction is it moving? Okay? So there's different ways that we could define the motion of the beach ball. Okay? We could look at its interactions. How does it interact with different surfaces? Maybe when it hits, well, in fact, when it hits the projector screen, what's going to happen to it? Any physicists? What do you think is going to happen when the beach ball hits the projector screen? It just drops. Why does it drop and not bounce off? The screen moves away from it. Okay? So we end up seeing different interactions with different materials. Chemistry is ultimately doing the same thing. Our molecules interact differently with different parts of their environment. Okay? Reactions, okay, are a particular subclass of interactions. When we look at a reaction in chemistry, we're looking at two beach balls coming together and hitting each other. Okay? And if it was just two beach balls, what happens when they hit each other? They bounce away from each other. Okay? If we were going to look at a reaction in actual molecules, what was another possibility? What could those two beach balls do when they hit each other? They could connect to each other. Okay? And we form a reaction where we now interact these two with each other and they form a bond. Okay? So we could do that with the beach balls by coating one with Velcro or both of them with Velcro on different parts of it. And if that beach ball happened to hit in the perfect alignment, we might see that those two bond to each other. Okay? Bit slow. Okay, so this is what we just talked about here. Looking at the beach ball. And we go through and look at controls. So what things are going to contribute to those things? Okay? Energy, the energy of the classroom. How many people are yawning versus how many people are actively jumping up and smacking the beach ball? Okay? That wasn't a targeted anything, just so you know. It's okay to yawn. We could look at concentration. What happens if we threw more beach balls in the ground? Probably on the ground, they'd probably all fall to the ground. But if we increase the amount of beach balls in the classroom, we might expect more interactions between those beach balls. Okay, more of them impacting each other. Okay, what about individual barriers to the reaction? Okay, let's say only half the class, since there's less people over here, we'll say you guys are cooler, like a little more space, right? Okay, over here is the energetic side where the beach balls are actually moving. Okay, where people are actually hitting it. When we move over to this side, you guys are all tired, don't want to hit the beach ball. Okay, so if the beach ball crosses over here, it kind of dies. Okay, it doesn't progress. How could we speed up the reaction? Well, we could prevent the beach ball from transferring from one side to the other. We could put a barrier in between you two. Okay, so over here, we can get the beach balls interacting with each other. Over here, they just kind of stop moving. If we drop that barrier, more beach balls can shift across, and now maybe we don't see any reactions. Okay, so there's different things that can contribute to barrier or preventing the reaction occurring. We could also potentially increase the likelihood of the reactions occurring. Okay, how could we increase the beach balls bouncing through this classroom? Okay, we could change the location. Instead of it being in a classroom, sitting down, staring blankly at somebody that's talking at you, okay, we could make it at a beach. Okay, hence the beach balls, right? Might as well make it exciting. Okay, if we shift it to a beach, that might change the interaction. Okay, we could push in time. We could go to the graduation, your graduation ceremony, when you're finally glad that you don't have to listen to someone talk at you for 2 hours. Okay, we would expect the beach ball to change its interaction and what it could potentially do. Okay, so what we're going to do is now push this into an actual example. Let's now shift away from the beach balls and look at chemistry. Okay, you'll see lovely animations as we go through some of these. Okay, some of them better than others. If I stole them from the internet, they look better. If I made them, not so much nice. Okay, what type of reaction is this? We've got a combustion reaction. Okay, that's good. So we're looking at some organic material reacting with oxygen to convert over to water and CO2. Okay, so if we took a look at our reactants in this reaction, we've got a log. Okay, where's the oxygen? It's in the air. Okay, how do we know it's in the air? We could go back to the equation and say we specified phases. Personally, I hate phases. I find them frustrating to always include, but there's useful information there. We know it's in the air, so in this single picture here of the log, we also have oxygen. So why, when I take a look at my reactants here, do they not look like the reaction's actually occurring? Why does this log ever exist in this state? Why is it not instantly burning? Okay, for that material, or for that matter, there's another organic material that we could look at. We're all made out of organic materials. This reaction is extremely favorable. Hence, once you start it burning, it runs out. Okay, and we end up losing the log entirely. We are all reacting with oxygen as we speak to generate CO2 and water. How do you know we're generating CO2 and water? Hopefully you remember from biology, and sorry for those of you in front, we respire, okay, or we expire. CO2 and water is expelled from our bodies every day. Okay? So why are we not instantly all on flame? Why do we even exist? Well, there's some barrier to that reaction. We have to initiate that reaction and allow it to actually start. Okay? That barrier is one of the things that, or is the thing that determines kinetics, okay, in our reactions. Okay? What could we do to initiate this reaction? Friction works. Definitely a lot more difficult than I was hoping to get out of that. But we could do friction, or we could do ultimately some form of heat, and friction is going to generate heat. So we could throw in a match, get something to start this fire, okay, or start that reaction. Once we've added that energy, we can now clear that activate or clear our barrier to the reaction, and our reaction can actually start. Okay? So once we've cleared that, we can now run. Okay? So what part of the log is actually burning? So now we're going to look kind of towards concentration and towards phases. Let's say we get this log actually started burning. What part of it burns? The outside. What about the inside? Okay. Eventually we get there, but it's not actually reacting at first. Why not? There's no oxygen there. Okay. We're limiting some of the reactant concentration. What happens if we went through and turned this into sawdust? Please say that's the next one. If we turn that whole log into sawdust, how fast would we expect it to burn? Should it burn faster or slower? Faster. Why? More surface area, which is ultimately looking at another thing for us, concentration. We've effectively increased the concentration, the surface where our material can interact. Okay? So if we look at the different phases, ultimately we want to avoid solids. Okay? Because solids have a surface area that allows us to do our individual reactions. So if we looked at the concentration or the amount of that log, okay, it's a little bit difficult to interpret because the inside can't actually react. So when we're going to look at our kinetics, and in fact most of our reactions, we're going to avoid solids and we're going to look at gases. Why would gases work really well? It's maximum surface area, right? We can't get any more surface area than an individual molecule on its own. We can also look at solutions. Why would solutions work? The exact same reason. When we look at a gas, okay, in particular if we say oxygen, oxygen is in this room. Is it the only thing in this room? No. So really we have oxygen dissolved in another species. Okay? So just the same as if we took salt and say dissolved it in water. Okay? So solutions and gas phase systems end up reacting very, very, very similarly. Okay? At least to a first approximation. Which is why we end up working with a lot of our kinetics and a lot of our chemistry reactions in those two phases. They're much easier to work with. We don't have to worry about this surface area problem. Okay? And that's kind of the nature of our reactant. We're pushing to solutions and gases. Okay? Is there something that we could add to this reaction to make it go faster? Okay, we could add gasoline. Okay? Or fire starter. What is that? I think I wrote it there. Oh, fire starter. Nice. What is that? It's not fire starter, is it? Lighter fluid? That's a little bit better. Maybe that's what I was thinking of. Okay? So we can add something else to this reaction. How does that actually speed our reaction along? We end up changing the overall reaction. So when we add fire starter, it's a lot easier to ignite that. Once that's ignited, that can then start up the burning of our wood. So what we've done is change the reaction. And in the process of changing that reaction, we've minimized or sped, sorry, I don't want to get into minimize yet, we've sped our primary reaction. Okay, so what we've done is added a catalyst. Okay, we've sped the reaction by adding another contributor to it. Okay? Whoops, I meant to get rid of that. So how do we monitor all of this? Okay, with the beach balls, it was relatively easy. We could see them all, okay? Or we can pretend to see them all. But what happens if we increase the amount of beach balls? Okay, if we drop all the way to, say, chemistry levels, okay, we're looking at relatively large amounts of molecules. So if we had 100 beach balls in here, we could still probably manage that. Okay? I think I can count that high on my fingers and toes if I use a couple other people. Okay? So I can get a reasonable number for the amount of molecules interacting with 100 beach balls. But if I drop down to the molecular level of a piece of wood, the individual molecules within that, instead of there being 100 molecules in here or 100 beach balls, we're looking at something on the order of 10 to the 23rd atoms in here. or molecules. That number is now so vast and so massive that it becomes too difficult to interpret, and we have to come up with different ways to monitor our reactions. Okay? Okay, so ultimately what we want to do is come up with some way to monitor a characteristic change. Okay? And we'll make that relative to something else. So when we looked at our beach balls, we could look at speed. Okay? If the beach balls interacted with each other, okay, we could look at how many interactions we get per unit time. So what we've now developed is a rate, which is ultimately what kinetics are. Okay? And if I was a better artist, I'd make that a little nutshell looking shape at the bottom. Right? It's kinetics in a nutshell, rates. I got one person laughing before I had to explain it. Most of my jokes need explaining. I think that makes them good, right? Okay, so what is a rate? It's ultimately any comparison or any change with respect to some unit of time. Okay? So you've seen rates before. You've got the speed of your car, miles per hour. You've got the drip rate on an IV. Okay, I think that's right, cc's per minute, fairly standard. We could look at the speed of an engine as opposed to the speed of the car. We get rotations per minute. Okay? Gravity. Gravity is an interesting speed. In that case, it's meters per second. So we're looking at the change of what we would expect to be a speed with time. Okay? And in that case, we end up changing, those of you who have already taken physics, instead of looking at that as a speed or a velocity, what do we refer to that one as? Acceleration. But ultimately, what is it? It's still a rate. Okay? It's still ultimately a velocity or speed, but because we've got that double time in there, we end up changing our interpretation a little bit. Okay? Ultimately, all of these are conversion factors. All we're trying to do is convert one unit to another. Okay? Which, if you go back to 151 and look over all your material, everything you did in 151, beginning to end, was conversions. At no point did you do anything other than conversions. Gas laws? Gas laws aren't conversions, right? What did you do when you did gas laws? You converted one unit to another, atmosphere to liters. Okay? We had to do multiple different conversions and account for multiple different things, but they're still ultimately conversions. Okay? So we kind of have the nature of the reactant covered. We've got that idea. Now what we want to do is kind of look at what we can monitor for our reactions. Okay? So if we're going to watch an individual reaction, what we can do is look at a concentration and we can look at time. Those are the two big things that we can watch. Okay? Yes?
Question where it says catalyst, it says it's never consumed in the overall reaction. But say, for instance, you threw gas.
I was waiting for you to say that. Technically, that's not a catalyst. Yeah. It was an example to get you to see that, get the idea of what's happening with it. But that's technically not a catalyst because it is consumed in the reaction. Way to call me out on it. Okay? Catalysts are a little bit more difficult to look at. Most of the catalyst reactions or catalyzed reactions are just a lot more complicated to look at. I can't just show a nice little picture that summarizes it. Okay? We'll talk about catalysts briefly towards the end of the kinetics chapter. Okay? But ultimately, that's all you really need to know, is that they change the reaction, which is ultimately what our gasoline was doing, but in the process, they're not consumed. Okay? So we'll look at a couple examples of catalysts, or your textbook looks at a couple examples of catalysts at the very, very end of the chapter. So if you're interested in that, you can go immediately jump to that and just read through it. Okay? So let's take a look at a chemical reaction. So this one I picked from your textbook. So some of the examples I've looked at. Whoops, don't look at that. Okay, here's our reaction. Okay? How could we monitor this reaction? So this is where we're going to start to look at more difficult questions. Because when we look at the textbook, they just tell us how we monitor it. You got any ideas how we could monitor this?
How quickly the reactions disappear.
How can you tell the reactants disappear?
It forms products.
How can you tell the products are formed?
Physical changes.
We could look for physical changes. Okay? So ultimately, yes, we do want to monitor the changes of our reactants and our products. But how do we physically see and do that? When we look at the lecture, we oftentimes just tell you, oh, this is what we're doing. Okay? When you move into the lab, you have to think a little bit more about how that experiment is built and put together. What can we monitor? Okay, so now we've got an idea of physical changes. What physical change could we monitor? What's that? Odor. Okay, now I got you. So we could try and look for smells. Okay. Problem with smell, can we quantify our smell very well? No. We could say it smells a little to now it smells a lot in this amount of time. That's very, very difficult to quantify.
Color changes.
So we could look for color changes. Anybody know the physical states of any of these molecules? So smell would have worked for this species, formaldehyde. Whoops, formic acid. Okay, but we can't monitor the smell very well. Physical state of bromine. Cheat. Isn't it? Oh, I can barely see it, so maybe you guys can't see it either. What do the colors mean on that periodic table? Physical state. Bromine is what color? Blue. What does that mean? It's a liquid. Okay. So that's interesting. We've got it being a liquid. Okay, but what else could we do from that? Anybody else know anything about its physical state? Could look at weight. That's going to be difficult to monitor the small changes that are occurring between here. What does it look like? Bromine is a brown liquid. Anybody know the color of bromide? Colorless. What happens in the course of this reaction? A color change. We go from a brown liquid or a brown solution to a colorless solution. So we can monitor the absorption spectrum. Okay, you guys did this, I think you did it in 151, where you looked at color changes and related that back to a concentration change. Wait, did you do that? That might be this semester. I think you do that this semester. We're going to do that. We're going to take a color change and use that to monitor our reaction. For that to really work, we would have to assume the rest of those are colorless. Okay? So what we could do is go verify. Yes, all of those are colorless, except for the bromine. Okay, so we could monitor this reaction via color. What else could we do?
Temperature.
Okay, we could look for temperature. Most reactions have very subtle differences in temperature. So a very small change could result in a very large reaction rate, and it's not going to be easy to monitor that subtle change. Okay, but that's not a bad idea. You guys have come up with some really interesting but difficult ideas.
The formation of gas or solids forming.
If we take a look at this overall reaction, what's that last product? We've got CO2. What's special about CO2? It's a gas. So in the course of this reaction, what happens? We start to build up pressure within the reaction. CO2 starts to form. So we could monitor the course of the reaction based on the pressure change. Okay, CO2 forming. Okay, any others? One last more that we're technically going to look at a little bit later. We could look for a precipitate, except in the course of this reaction I haven't shown any precipitates forming, but that's a good idea. We could add a precipitate indicator, if we will.
You could measure it with a pH meter to watch the formation of the hydrogen.
Right idea, and in fact that's everything I was going to add to it. We could monitor the pH, okay, which technically you haven't learned officially yet, but pH is a measure of the concentration of hydrogen ion, or H+. So we could monitor the pH change for the reaction. Does it increase? Does it decrease? How does that end up resulting back to our concentration of H+. Okay? So there's a variety of ways that we could end up looking at this. Okay, so now we can go back to what I had initially. So we could go through and we could graph, or sorry, not graph yet, generate a table. Monitor the reaction with time and determine our concentrations. Fantastic, that's great. How easy is that to interpret? Is there anything wrong with any of that data? Anything jump out at you? Oh my God, that data point is awful. Out of order? I don't think that's the case. Could be. I did make it. Let's change it up. What happens if we graph it? See a very odd point floating up out there. Okay? So we could go through and look at raw data and collect raw data into tables and tables of stuff. And that works great, except that we can't draw conclusions from it very easily. Okay? We would have to go through and individually compare each data point all the way through. Okay? And with that amount of information, that's a bit painful. Okay? So a mathematician came along and said, look, you're being an idiot, just graph it. Kevin went, oh, that's nice, I'll just graph it. And now when we graph it, we take a look at our results and we say that data point doesn't make sense. Okay? How can we eliminate that from our experiment? There's two ways. There's the technically not so nice way, which is pull out an eraser. We erase it. We could even get it even worse than that. We could say, well, it's probably supposed to be this. And just change the number. Okay? Neither of those ways are particularly good ways to do it. Okay? Those are technically anti-science because we don't know that that data point was necessarily a mistake. Okay? That could be a very real data point, and we don't know that. So what we would have to do is come up with some way to eliminate it. You can go back to statistics, okay, and eliminate it in that fashion, or we could go through and everybody's favorite thing when you get into lab, you redo the whole experiment. Okay? So if you ever go into grad school or PhD things kind of along those lines, that is one of the banes of all graduate students' research. You have to be able to repeat the experiment and get the exact same result. Okay? Very, very, very rare. Okay? So let's just say we repeated it, came up a little bit nicer. Okay? So we could now start to interpret it and look at what things changed. Okay? Assuming I plotted this all properly. If we take a look at the bromine concentration, what happens to the concentration of bromine during the course of the reaction? It decreases. Does that make sense for it to decrease? Yeah, why? It's a reactant, and it's ultimately changing into the products. When we look at our products, there's no bromine. Okay? We could also try and monitor the other two that we talked about, hydrogen or CO2. Okay? And what happens to those? What happens to the concentration during the course of the reaction? It increases, which makes sense again because those are products. Okay? So what we're trying to do is put this data into some way that we can interpret and see easily. Okay? And that's one of our first goals. Once we've got the graph, we can then start to go through and determine rates. Okay? Our rate was a change with respect to time. Okay? How could we determine a rate for this? Let's look at the bromine. I want to know the rate of bromine through the course of the reaction. What would I do? What's that?
Derive it.
Okay, how? 2 points on the line. If I said the course of the reaction, we're looking at these 2 points. So what would I do to derive that? I'm going to take my concentration change during the course of the reaction. Uh-oh, we can see how well I can read a graph. I'm going to say that's 0.004. Okay, so during the course of the reaction, I started with, or I ended with 0. How many zeros? One more. 4 minus what did I start with? Okay. Over the course of time, what was the time difference? 400 minus, what did I start at? 0. And I could go through and calculate that. Okay, because I just picked 2 random data points, believe it or not. How many of you have a calculator handy? You didn't have to get it, I just want to know if you had it handy. Oh, 2 of you actually already have it out. Okay, you can give me the number then. I was just going to make something up. What do you get? Okay, what's that negative mean? What's that? Decreasing. So that negative is ultimately an interpretation. The mathematics gives us the negative. We take that negative and interpret it. Okay? That interpretation is that our concentration is decreasing over the course of that time. Okay? So this is one of the beginning points of looking at how mathematics and English and chemistry all interrelate with each other. We have to be able to interpret that negative to mean something. Okay? If we haven't set up our mathematics to assume or imply that interpretation, we would have to show the negative. Okay? What if I wanted to change and look at a different rate? What if I looked at this point between those two? Would I expect the same rate? No, it's different. How can we tell that? Well, when we go through and do this calculation, graphically what we're saying is we are only looking at, how many of you can draw a straight line? Good. Neither can I. We're looking at, oh my gosh, that's pretty close. Okay? The distance between those two. You'll notice it doesn't completely match with our actual reaction. So our rate is actually changing during the course of the reaction. Okay? And that change is ultimately what we're going to look at when we talk about this tomorrow. Okay? So